Ready?
3, 2, 1. Action.
So, ladies and gentlemen, welcome. Today we are talking about trigonometric ratios. All right, ratios are like fractions, right? In right triangles. So the first thing I want to do is just talk about some lingo.
Lingo? That's a good game.
Limbo.
Oh, I
That's
thought you
maybe
said
what you're thinking
lingo.
about. I did say lingo.
Lingo.
Limbo is a good game. Lingo is a game as well?
Limbo's pretty sweet.
Apparently, I did not know this.
Don't wait.
So check this out. Here's a right triangle. Typically, C will be referred to as our angle. That's the 90 degree. In terms of naming conventions, little c is opposite big C, little a is opposite big A, and little b is opposite big B. So what I want to talk about is if I'm looking from angle A's perspective, all right, from angle A's perspective, if this is my theta, well, C, I think I've already used the word, is the hypotenuse.
Hypotenuse.
Hypotenuse. All right. A and B are both legs.
I've never heard of that terminology.
All right. And A, from theta's perspective, A is the opposite leg.
Be right back.
And B is the adjacent leg. Excuse me, sir, please. Come on now. Come on now. Let's just let us continue, if you'd be so kind. So I just want to point out that both A and B are going to be acute angles. C is your 90 degree angle. The sum of all three is 180, blah, 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 right? All sorts of good stuff. Now, it turns out our trigonometric ratios are going to be from perspectives of one of the acute angles. So our trig ratios, if I wanted to say, well, I guess I'll leave that up. The first trig ratio is abbreviated SIN, which is read as sine of theta. All right.
Which you can find on your calculators.
Yep, and that is a button found on our calculators. And sine of theta is permanently referred to as the ratio of opposite over hypotenuse. Okay, so it's the ratio of two sides from that angle's perspective. For cosine of theta, abbreviated cos theta, read out loud as cosine theta. Does anyone know what cosine's ratio is? From theta's perspective, it's the ratio of the adjacent leg to the hypotenuse. And tangent
what is that?
theta.
Jeez. Tan, which you can also find on your calculator.
Correct. Also found on our calculator. Tangent theta is the ratio of opposite over adjacent. All right, and it turns out that these ratios are consistent. So the sine of a 30 degree angle is always going to be the same ratio. No matter the size of the triangle, the ratio of those two sides will be the same. All right, so those are the primary trig ratios. Now, I don't know if you've ever heard of this abbreviation, but SOHCAHTOA is often an abbreviation used to remember those, right? So sine is the ratio of opposite over hypotenuse. Cosine is the ratio of adjacent over hypotenuse. TOA tangent is the ratio of opposite over adjacent. So, SOHCAHTOA, right? So that is the idea. So let's do an example with these. Example. Saratoga. Ticonderoga.
I went to that place, that fort.
Sara Lee. Yeah, I've been there too. So anyways, so find the trig ratios.
I already know how to do this.
Excellent.
Key taught me.
So suppose this is my triangle. Here's my 90-degree angle. Suppose this is 3. Suppose this is the square root of,
Come on, really?
let's do 13. Yeah. Yes. So let's see. And let's say that I want to know the trig ratios from angle A's perspective and from angle B's perspective. So if I want to find out what is sine of A,
Well, A is a...
where
Is
A
the
is this
opposite.
angle, so sine is the ratio of opposite over hypotenuse.
Yes.
So that'll be opposite is the square root of 13. And to find the hypotenuse, it was unlabeled, but you are absolutely correct. I can use the classic Pythagorean theorem.
What? Well, no.
It's okay. It's okay.
Hate this.
So let's see. 3 squared is 9. Root 13 squared is just straight 13 equals c squared. So c squared is equal to 21. So c is the square root of 21. Oh, I believed you. It's okay. It's okay. No. No es más malo de matemáticas. So, square root of 22 is the value of c. All right, so I can plug that in right here, right? So this would be the ratio of square root of 13 over the square root of 22. And technically, I couldn't leave it like that.
So A is 20, square root of 22.
No, c is the square root of 22. Little a is the square root of 13. The sine of a...
C is square root of 13.
Nope. This would be angle C. Side C is the opposite of angle C.
So that's side.
Side A is opposite of angle A, and side B is opposite of angle B.
So that's B.
Hey, don't bring me into this.
So root 22, root 22.
Oh, we got a funny guy.
So let's see. 13 times 22. I don't feel like doing that. It's 286. So it'd be the square root of 286, 20 seconds. Now, I wonder, is that divisible by 4? No. That would make sense, yeah. I don't think it's reducible. Actually, old computers used to get 286 processors, I think, is what used to exist back in the day. So there's the value of sine of A. Okay, so now we've got some values. Let's keep cruising. What if I want to figure out what cosine of A is? So adjacent from A's perspective is the 3 over the hypotenuse is root 22.
What?
These will actually help us later on in solving for missing sides or angles of triangles. And for the beginning of this chapter, we'll be working specifically with just right triangles, which if you know 2 sides of a right triangle, you already know how to find the third using Pythagoras. However, with these, we'll be able to know a side and an angle and be able to find everything else about the triangle. Or, eventually, by the end of the chapter, we'll be finding missing sides and angles of any shaped triangle, whether it's right or not, or wrong. So, 3 over the square root of 22 simplifies to 3 roots of 22 over 22. I haven't seen a bingo in a while.
What's a bingo?
You're the one that invented it.
I said lingo. Oh wait, bingo. Oh right. All right. It took me a while. All right.
That's funny. Let's see, tan of A. How do I find tangent of A? What's his tangent? Toa? No, Toa, not Teo.
It's opposite over adjacent.
Opposite over adjacent, right? So that would just be root 13 over 3. So those are the ratios there. And now, what is, quickly, what would the sine of B, the cosine of B,
Jeez.
also read as Cosby, am I right?
Ah, you jokester. Is he still alive?
Yes. Actually, he, in his 80s, has still been, like, touring and doing comedy shows. Pretty crazy. Yeah. Like, and doing, like, 2 to 3 sets a night sometimes. Craziness. He's a pretty hard worker, I guess. Sine of angle B. So this time from B's perspective, which, by the way, I would not expect that angle B is the same as angle A. However, if it was, all of the ratios would have been the same. But I don't think they're going to be the same. Actually, does anyone know the relationship between angles A and B?
The opposite.
The hypotenuse should be half.
In a 30, 60, 90 triangle, I suppose would be that. But right, angles A, B, and C add up to 180, but angles A and B are complementary of one another. They add up to a 90
That's what I
degree.
said.
Oh, I'm sorry, I didn't hear it. I'm sure we can roll back the tape if we have to. So sine of B, from angle B's perspective, the opposites and the adjacents have switched positions. However,
Dot.
hypotenuse is always the same. So sine of A, what's the ratio for sine?
It was
Opposite over hypotenuse. So this one would be 3 over root 2. Sorry, root 22.
Okay, I was confused.
However, wait, I calculated that already. That's going to be 3 roots of 22 over 22. Cosine of B, Cosby. What do we got? From cosine of B, what's the ratio for cosine?
Cosine is adjacent over hypotenuse.
Adjacent over hypotenuse. So that's going to be root 13 over root 22.
And you've already done. Oh, no, you have. Yeah, you have.
Yeah, we have.
286.
That's root 286 over 22. And tangent of B, what's tangent's ratio?
It's opposite over adjacent.
Toa, so opposite over adjacent, so 3 over root 13. Which is, in this case, 3 roots of 13 over 13. So I just want to point out, we could find all of these. If I know 2 sides of a right triangle, I can find the third side using Pythagoras and his theorem. And then all of these ratios exist. And like I was saying earlier, a sine of a 30-degree angle in any triangle is always the same. And the ratio of sine of 30 degrees is always the same ratio. And actually, that's why, and these values actually would have originally were kind of documented down in tables, similar to the logarithm tables that I gave you a while ago. That would have been Math 3, previous course. But I do actually have those tables done out. Actually, maybe I'll even show you.
Last year.
That's the last semester.
No, you usually say last year.
I know.
Doesn't feel right. Anyways, whoop.
Yeah.
All right, senor.
Just weird. Thanks.
So,
Whoa.
so let's see. So here's just kind of a table with different values on it.
No.
Oh, what did I do?
I don't know. I just lost my pen now. Did you
Oh.
mess up? Did you not double side it?
Oh, blast.
You didn't double side it, did you?
I didn't double-side it.
Oh my
So what I've got here is sine and cosine for different degrees. Oh well, I'll figure these out later.
Dude.
I don't know. I'll tell you what, I'll just pass them out and you guys figure it out.
You can just staple them together.
You figure it out.
Where's
There we
the
go.
other half? I want the other
It's
half.
every other page is a different sheet.
No, it's not. Yes, it is.
Yes,
Well,
it is.
where's that back hand?
So, don't worry
I want
about
the
it.
hand on the back.
Oh, that one's coming later. So, so someone went and calculated, for instance, what is sine of 1 degree? And apparently it's the ratio 0.0175. All right, what is the cosine of 1 degree? It's 0.9998, right? And they've gone through and calculated all of these, and this is how back in the day they had to do these things because they didn't have calculators. Fortunately for us, we do have calculators. So if I want to figure out what sine of 1 degree is, hopefully I'm in degree mode, and I get 0.017, and that is what I got right there. Apparently it was rounded to 5. Yeah, which would make sense, because the 5 would make that 4 go up. So we've got these stored in our calculators, but if for some reason you did not have a calculator, this table is available to you. I also have some crazy little notations hiding around. We'll talk about those later in this chapter, perhaps. Also, this one you'll have to memorize.
No!
Good stuff. So that is how they did it back in the day. They actually used to have these tables printed in the back of math books as well in order to make that accessible, whatever. Here we go. So,
So there are only 2 sheets we need?
yeah. So it turns out not only are there the original 3 trigonometric identities, but there's also reciprocal trig identities. Sir, you're standing in my way. Sir, I can't see. All right, so the reciprocal trig identities, if...
One, do you have your 2?
All right, so sine is opposite over hypotenuse, right? It turns out there's CSC of theta, which is read as cosecant theta. All right, CSC. And that is the ratio. If sine is opposite over hypotenuse, this is hypotenuse over opposite. Okay? And then there is secant theta. All right, abbreviated SEC. So secant theta. That's how you would read that out loud. And that is the reciprocal of cosine. So if cosine is adjacent over hypotenuse, then this must be hypotenuse over adjacent. By the way, the word adjacent just means touching side by side. Like, for instance, New Hampshire and Vermont are adjacent states to one another.
Where we live. Smart.
I didn't specify that we lived in either of those states.
Good stuff.
Cosecant,
you gave it
secant,
away.
and cotangent of theta. Cot theta. Read as cotangent. That's the one that makes sense. Because tangent and cotangent. Cotangent is the reciprocal of the tangent function. So if tangent is OA, opposite over adjacent, then cotangent is adjacent over
It's cotangent.
cotangent. Yep. Over opposite. So if I had some sort of acronym to remember these, it would be CHO, SHA, COW. Which is
Choshakao.
not...
Something like Chinese.
No, it's just me.
Choshakao.
That's just me.
Doesn't that sound Chinese?
Anyways,
Chow Shai Kao.
so it turns out these reciprocal identities also exist. And we'll end up using some of those as well. So let's do an example. So if cosine of theta is 3/4, find secant of theta. So what do you think secant theta would be? Anybody? What was that? Yeah. So secant theta is the reciprocal of cosine, so that would be 4/3, right? Now, actually, with the same information, would you be able to figure out what tangent of this theta was? I want to point out we could actually draw a picture. All right, so I don't know the shape or size of this triangle very much, but if this is theta, if cosine of theta is 3/4, what side is 3 and what side is 4? Or at least has the ratio of 3 to 4.
The hypotenuse is 4 and the adjacent is 3.
And the adjacent was 3. So if I wanted to find tangent of theta, which is the ratio of opposite over adjacent, I would have to figure out what is the length of the opposite. How could I do that? Now it turns out the hypotenuse is always the c in the Pythagorean theorem. So when I do this, I'd have to be very careful. A squared is equal to, what's that, 7? So A is square root of 7. Now technically when I root both sides, yeah, I agree. Algebraically, negative square root of 7 is an answer to this equation. However, geometrically speaking, we're talking about a length here, so it would be positive. Right. So tan theta for the very same triangle would be root 7 over 3. All right. What if I wanted, let me ask you one more question. What if we wanted to know what is cosecant theta? Cosecant is the reciprocal of sine.
So it's a hypothesis.
No, hypotenuse.
Only
Quite all right.
Opposite. So for
Wait. It's the reciprocal of sine. Sine is opposite over hypotenuse. Cosecant is hypotenuse over adjacent. So from theta's perspective,
SCS.
that'd be 4. Wait a minute. Wait.
Yeah, 4.
Sorry, did I say adjacent when I underlined that?
Yeah,
I did.
that's what it confused me.
Hypotenuse over opposite. Wow, classic. So that'd be 4 roots of 7, or 4 over the root of 7, or 4 roots of 7 over 7 when I simplify the radical. So I just want to point out, even with a single fact, we can actually branch out and find a bunch of the other ones, which is kind of helpful at times. Now, it turns out some trig values, all right, I gave you that table there, but some of these we're going to have memorized. Is right.
Bleh.
Bleh.
So check this out. Consider. Now someone mentioned 30, 60, 90 triangle earlier.
And me.
All right. Here's a 45, 45, 90. And then 30, 60, 90. I'm not a fan of
that's
that.
straight line. Why don't you use your tool that makes a straight line?
Because I'm better than that.
That's why you make the little
guy.
60, 30, right? 30, 60, 90, special right triangle. Okay? And one of the ways I think about the 30, 60, 90 triangle is if I drew an equilateral triangle and cut it in half, drew its height, I would get a 30, 60, 90. And that'll help us out in figuring some of this stuff. So let's see if you guys know the ratios of a 45, 45, 90. So if this is x, what is the other leg measure? Also x. And what is the hypotenuse compared to those? X times the square root of 2. The hypotenuse is the square root of 2 times longer than the legs in a 45, 45, 90. And actually, sometimes people think that those would all be the same, right? They, for some reason, assume that the diagonal of a square is the same as its sides, right? Imagine this being a square that I cut in half across the diagonal, right? Those would all be x's, and then x times the square root of 2 would be what I'd get there. I could actually solve that using Pythagorean theorem. X squared plus x squared equals c squared. C squared would equal 2x, and then I'd 2x squared, and then I'd root both sides and end up getting that ratio. All right, how about this? For the 30, 60, 90, if the shortest leg is x, what else could you tell me? What is 2x? The other leg? Not quite. Well, think about if this is x, what would this length have been?
X squared.
No.
X to the square root.
No.
I don't.
This would have been 2x, right? Because this cut that in half. And if this is 2x, then that means this is 2x. So the hypotenuse is 2x. So that's where the 2x was coming from. So you did have some memory there of 30, 60, 90s. And now, even trickier is, what is the height here? Does anyone know how to do that?
X squared plus 2x.
Oh, nope. I lied. The height would be like a squared plus x squared equals 2x all squared. So a squared plus x squared equals 4x squared. Subtract x squared both sides. A squared is equal to 3x squared. Root both sides. A is going to equal x times the square root of 3. And this is true for every 30, 60, 90 triangle. So the longest leg is the square root of 3 times longer than the shortest leg. So let me ask you some questions based off of this information. 30. Well, actually, eventually we'll extend this to some other ones, but 30, 45, 60, and 90. Let's make this little chart here. So what is sine of theta? All right, so that list is theta. What is sine of theta, cosine theta, and tangent theta?
Because I'm living it out in town.
So using our triangles up top, what is sine of 30 degrees? So, sine is the ratio of what now?
Opposite over hypotenuse.
Okay, so from this 30-degree angle, the opposite's length is x. The hypotenuse length is 2x. What does x divided by 2x equal? 1/2. The x's would cancel out. So sine of 30 degrees is a half.
That's like a Z.
Yep, but it's not a bingo. What is sine of 45 degrees?
Still good.
Gentlemen. Sine of 45 degrees. Here's a 45-degree angle. So opposite over hypotenuse. I will get x over x roots of 2. 1 over the square root of 2, which is equal to... Oh, nope, I'm writing that in the wrong spot. 1 over the square root of 2, which is root 2 over 2. So that's two different ways to write it. 0.707, roughly. What is sine of 60 degrees? Where's the 60-degree angle? Right here. So sine is opposite over hypotenuse. So x roots of 3 divided by 2x. No. Opposite was root 3. Hypotenuse 2. Square root of 3 over 2. I think that's 0.866 roughly, if I recall. Oh, actually, 90 degrees we don't know how to do yet, and neither do we know how to do 0. Those we'll know how to do later.
In tomorrow's lesson.
I don't remember. Someday. Yeah, probably tomorrow. Cosine of theta. All right, cosine is the ratio of what?
So, adjacent over hypotenuse.
Adjacent over hypotenuse. So where's a 30-degree angle? Right here. Adjacent is x roots of 3. Hypotenuse is 2x. So cosine of 30 is root 3 over 2. Cosine 45 happens to be the same as sine of 45. Why is that? Yeah, because the adjacent, right, and the adjacent and the opposite are the same value. So if I do adjacent or opposite over the hypotenuse, it's going to be the same ratio. So for 45 degrees, they're the same. And what is cosine of 60 degrees? X over 2x, which is a half. Right?
Yep.
So,
There's so many things.
yeah, so looking at these, notice that sine of 30 is the same as cosine of 60.
Sine of 60 is the same as cosine of 30.
Yeah. Turns out there's a relationship there. It has to do with the fact that these angles are complementary, right? So 30 and 60 are complementary with one another. And sine from angle 60's perspective, right, would have been opposite over hypotenuse. But cosine from angle 30's perspective would have been adjacent over hypotenuse. And it's comparing the same two numbers from two different perspectives. All right? And it has to do with the fact that those are complementary. So it turns out later we'll realize that sine of 90 minus theta is equal to cosine of theta. Kind of this little relationship, the fact that my angles are complementary to one another. But let's keep going with tangent, and we might end up calling it a day. A day. So tan theta is the ratio of what to what?
Can you show that well?
We'll get back to that. Opposite to adjacent. So tangent of 30. Opposite to adjacent. So, yeah, so 1 over the square root of 3 or square root of 3 over 3. Let's see, let me write a better 3 there. There we go. How about tan 45? X over x, 1. Wow. So, and what is tan of 60 going to equal? Opposite over adjacent, square root of 3. So yeah, so we're eventually going to have these all memorized.
Those numbers?
Yep. But
Why?
because we're awesome.
No.
And we'll use these all of the time. Todo de los tiempos.
in what real life? Like doing what?
In math class the rest of the year.
But in real life.
And in pre-calculus. And in calculus.
But I mean like a job.
Don't worry about it. But I wanted to point out, that's true, that we can derive them just by drawing our two special triangles. You can derive all of these. So that would be a very slow way to find them if you didn't remember them. But I'll also teach you a little hand trick, probably mañana, once we know 0 degrees and 90 degrees. It'll be good. So for now, just understand that these are ratios that are common amongst all triangles. So if I have a 22-degree angle, the sine of 22 degrees is always the sine of 22 degrees, no matter what size those triangles are. All right? And then even if I don't even have a triangle, which we'll talk about later, sine of 22 degrees is still sine of 22 degrees. So it's a ratio that will be helpful. And I guess in terms of ratios that we've used before, because I think this is a little bit abstract, having a list of a whole bunch of ratios, technically pi is a ratio that is constant all the time for circles. Do you guys know what pi comes from?
3.14.
Well, yeah, but where did it come from?
Comes from.
It's a ratio. 2 pi r is equal to the circumference. So what's pi equal to?
Radius. The moon. The sun.
Circumference divided by 2 would equal pi r.
It's 3/4 of the circumference.
Here, this is bonus content right here. All right. So you just told me a moment ago that circumference is equal to 2 pi r. How do I solve that for pi?
Well, you get the radius.
Divided by 2.
What's the diameter, or what's the
It's
radius?
a quarter of the radius.
Well, what's the radius?
Pi is equal to circumference over twice the radius. You also could say that pi is the ratio of the circumference to the diameter.
Okay, but what's the radius? Or the diameter? What's the number?
And that's true for all circles. So that's a ratio that we use all the time to solve facts about circles, right? And we're going to use these same kinds of ratios for triangles now. And these ratios are true all the time. So sine of 22 degrees, perhaps not as important as pi, but just as effective in its own universe if your universe was all triangles. So, all right.
And slow down.
Bye, Internet.